And coming up next, let's welcome Marcel, who works for Siemens Test and Embedded Analytics, and his specialization is the E-Trace Decoder.
Thank you. I will just set it. Okay. Hi, everyone. Thank you very much for the introduction. Today, I'm going to speak about unleashing the power of RISC-V E-Trace with a highly efficient software decoder. First, I will tell you about what trace actually is. Then I will speak about why would you use trace, what are the use cases. And then I will show you some results and API of our decoder implementation. I'll also mention how we approach the challenge of tracing any custom instruction. And at the end, I will wrap up with summary. So what is trace? It's a powerful technique that lets us monitor processor activity without interfering with its operation. Unlike traditional debugging methods like breakpoints or run control that needs to stop the processor, trace gives us a complete visibility into the processor's behavior while it keeps running at a full speed. Turning sampling on requires your CPU to perform additional operations. Therefore, it adds overhead on your application. Also, sampling does not provide full visibility. Trace becomes particularly valuable in modern applications where traditional debugging really don't work anymore. Think about complex SoCs with multiple cores, or scenarios where you need to understand your CPU to peripheral interactions, or real-time systems. You can't just hold these systems and expect meaningful results. It's especially useful for identifying suboptimal implementations and understanding complex systems behaviors. Best of all, trace can complement other debugging tools, working alongside run control, code coverage analyses, reverse debuggers, and quality assurance tools to give you a complete picture of your system's behavior. To summarize in a single sentence, it's a technique for monitoring the activity of your processor in an unintrusive way. This diagram shows you where the magic happens. It's a two-part system, hardware and software working together. On the chip side, we have the encoder, hardware that captures processor activity. But since we can't send all this data off the chip due to the bandwidth limitations, E-Trace standard specifies powerful compression technique that reduces the data by approximately 700 times. As shown in our diagram, this compressed data travels from the encoder through the buffer and off the chip. Then our software decoder takes over, decompressing this information to reconstruct the complete execution flow, giving us the full picture of what happened in the processor. Here is a specific example that shows why it is so important to have a trace encoder IP in a product. This slide was kindly provided by Richard Bond from Seagate. The challenge they faced was that when they got to the 50 terabyte hard drive capacity, the required positioning accuracy of a head was 2.4 nanometers. If you think about it, it's quite mind-blowing. When you are working with an embedded system, you don't have gigabytes of storage to save your debug information. Or when you are working with a real-time system, you can't just insert debug code into the main path and not to affect the function of the design. You can also slow down the drive. You always need to run at a full production speed. To debug and optimize the firmware, Seagate used Tessent Enhanced Trace Encoder alongside with other embedded analytics IP modules. In this case, the encoder has also a cycle-accurate capability, which provides additional information about how many cycles each instruction took to execute, and also where the stalls happened. This feature was important to allow optimization of performance-critical sections of the code, and the end result was 3 times reduction in computational cycles in a key matrix compared to the legacy core. Trace also plays a crucial role in silicon lifecycle management. As chips are deployed in the field, over the lifetime of its usage, there can be many problems that aren't immediately visible. Silicon problems like latent manufacturing defects, IR drops, thermal effects, and aging affect the functional behavior. These often manifest as mysterious software errors, underperformance, or silent data corruption that's particularly hard to diagnose. What makes Trace especially valuable is its ability to capture infrequent and irregular errors caused by these subtle silicon defects. By monitoring CPU instructions, bus transactions, and critical signals in real time, we can collect timestamp data that reveals the full story of the system's behavior. The real power comes from correlating this trace data with other SLM measurements. SLM stands for Silicon Lifecycle Management. PVT sensors, slug monitoring, voltage drop data, and built-in self-test results. However, it creates enormous amount of data at the system speed. Just a few lines of C code translates into hundreds or thousands of CPU instructions. This is why compression is a must. This integrated approach gives us unprecedented visibility into our silicon's health throughout its entire life cycle. The hardware encoder provides an impressive compression ratio up to 700 times just with the mandatory features. The optional extensions give a further boost to the compression. This chart compares encoding efficiency across a subset of M-bench tests measured in bits per instruction. Okay, but what it actually means, bits per instruction? You can think about it as how many bits the hardware encoder needs to send per each executed or retired instruction in the CPU. The yellow bars show our baseline encoding with extensions disabled, with average of 0.248 bits per instruction. The blue bars represent the compression with E-Trace extensions enabled, an average of 0.135 bits per instruction. The results show a consistent improvement across every single test. In summary, we achieve an average of 46% reduction in bits per instruction when using the extensions. This dramatic improvement means that more trace data can be captured and stored while using less bandwidth. It has a significant benefit for real-world applications such as silicon lifecycle management. Okay, but what is the performance of the software decoder when using the optional extensions? On one hand, the optional extensions allow better compression ratio. On the other hand, the software decoder must work harder to reconstruct the instruction addresses. This chart shows the decoding times in milliseconds across the same M-bench tests. The yellow bars represent the decoding times with extensions disabled, while the blue bars show the decoding times with extensions enabled. As you can see, across all tests using optional extensions results in slightly longer decoding times. Looking at the summary on the right, the average baseline time is about 108 milliseconds, increased to 150 milliseconds when utilizing the optional extensions. Next, let's look at how many CPU cycles are required per reconstructed instruction address. Even though the absolute number of CPU cycles is processor specific, comparing the relative differences should be more generalizable across different systems. With extensions, we average about 141 cycles per instruction. Without extensions enabled, we average about 141 cycles per instruction. And with the extensions enabled, the average is about 198 cycles per instruction. Looking at the individual tests, we see this pattern consistently. This roughly 39% increase in cycle count is the computational cost that you pay for better compression. Let's examine the algorithmic efficiency of our decoder through an empirical approximation of its big O complexity. The graph plots decoding time in milliseconds against the number of instructions processed, with a yellow line showing the baseline performance and the blue line representing performance with extensions enabled. What's particularly encouraging here is that both curves show a near linear relationship between processing time and instruction count. The particular implication is that the software decoder is predictable and efficient even as the number of instructions grows, making it suitable for managing real-life workloads during the silicon lifetime. We also designed a Python API to be as simple as possible. It makes the management of the hardware encoder and the software decoder features very straightforward. First, we create an obj dump from the program's ELF file. Then you just need 4 lines of code to get the program counter addresses. On the first line, we create a map of addresses to instructions. Then we create an instance of what we call processor trace, which takes care of all the configuration and decoding for you. Now we can start trace and iterate over the data in a simple for loop. The focus is on making it as straightforward as possible while still giving the user all the functionality needed. Moreover, each class has extensive doc strings and type hints, so there is no need to read PDF documentation. One of the key features that makes RISC-V special is the support for custom instructions. And naturally, being able to trace these instructions is essential for our work. From the day one, we knew we had to ensure that any custom instruction can be properly traced. Since these custom instructions can behave in various ways, we developed what we call a Custom Instruction Decoder API, or CID for short. Let me explain how it works. Users can implement their own decoder as a dynamic shared object based on our header files. Again, the API is very simple. There are just 4 functions that the user must implement. Create and destroy are pretty much what you would expect. They're handling initialization and a cleanup. Disassemble gives us additional information about the instruction and helps us to classify it correctly. And then the function next PC is basically telling us what the next program counter should be given the current context. This approach gives us flexibility to handle any custom instruction while maintaining accurate tracing even with the optional extensions enabled. So should you turn on optional extensions while tracing? Well, it depends on your priorities. Better compression versus faster decoding. When the extensions are enabled, an impressive 46% better compression is achieved compared to the baseline, which is shown by the yellow bar. However, this comes at a cost of decreasing decoding speed by about 39%, represented by the blue bar. This is because the decoder needs to work harder to reconstruct the program counter addresses. This presents an interesting choice for users when working with a limited bandwidth between the chip and the host machine, or if the storage is a concern, there is a huge benefit from enabling the optional extensions. On the other hand, if the decoding speed is critical and sufficient bandwidth is available, it's preferable to disable these extensions for faster processing. There is no universal answer here. It's about choosing what best fits your specific requirements and system constraints. Thank you very much for your attention. If you have any questions.
Thanks a lot, Marcel. Is there any question in the audience? Over there.
Yes, thank you for your talk. I was wondering if you were taking into account the frequency of occurrence of the instructions while doing the decoding.
Excuse me, can you please repeat the question?
Yes, sure. Do you take into account the frequency of occurrence of the instructions when you build your decoder in order to speed up decoding, or?
The frequency of the CPU where the decoding is happening, is that what you're asking for?
Well, you're decoding faster, you try to decode faster your instructions, and I was wondering if you were taking into account the frequency of occurrence of the instruction in the flow of instruction to do that.
No, this is not taken into account. No.
Okay, thank you.
But we can also speak later on if you are interested. We have a Siemens booth over there, and I will be very happy to answer your questions.
Thanks.
Thank you very much.
Okay, let's thank our speaker again.